Although the differential relay gives excellent protection for generators, transformers, and buses, it is not really suitable for feeder and transmission line protection. This is because the CTs would need to be located at either end of the line and the secondary leads conducted over a relatively long distance. This is expensive, and more important, the impedance of the secondary conductors could give rise to serious inaccuracies. As we shall see in future tapes, the differential principle is used for special applications. But a more common form of feeder protection is overcurrent. For example, a fault out here on this feeder would give rise to an overcurrent in the line. An overcurrent relay connected close to the breaker would detect this and could be set to open the breaker. The standard device number for an instantaneous overcurrent relay is number 50. Here is a typical instantaneous overcurrent relay of the clapper type. Its principle of operation is extremely simple. The CT measures the current in the primary line, and the CT secondary passes this current through the coil of the electromagnet. The resulting magnetic force pulls the hinged armature, that is, the clapper, against a restraining spring. If the current input to the relay is above the preset pickup level, then the relay contacts will close and so energize the tripping circuit. The pickup level can be adjusted by selecting taps on the coil and also by adjusting spring tension. Here's another type of instantaneous overcurrent relay, the plunger type. In this case, the electromagnet pulls the plunger up against the force of gravity. Again, the pickup level can be preset by adjusting taps and also by adjusting the position of the core. When current exceeds the pickup level, the instantaneous relay will operate within about 50 milliseconds, that's about 3 cycles, and energize the tripping circuit to open its associated breakers. This instantaneous action can prove to be a problem at times. For example, if a large consumer load is started, say a large motor, it will pull a considerable surge of current for a few seconds. This may well be high enough to trip the instantaneous overcurrent relay, and so isolate the whole feeder, including all other customers. To avoid this, the operating pickup must be set to a very high level, and certainly this would be adequate for protection of severe faults on the line. But how can we protect against low-level faults? This is achieved by use of the time overcurrent relay, device number 51. This is a typical electromechanical time overcurrent relay. Its main components are the electromagnet, the operating coil, the rotating disc, tripping contacts, and time dial. Secondary current from the CT is passed through the operating coil, which is wound around the central leg of the electromagnet. It sets up this magnetic circuit. The flux passes through the non-magnetic disc and then returns through the disc again to the outer legs of the electromagnet. In this condition, the disc will not rotate, as these two fluxes are in phase. However, by placing a shorted coil called a shading coil around one outer leg, a phase displacement occurs. Flux in this leg will now lag the other, and this causes the disc to rotate. The disc is normally held stationary by a retaining spring. Only when there is sufficient current passing through the operating coil will the disc start to move. That is the pickup level. Remember, the magnitude of current in the operating coil is proportional to the primary current along the feeder, which we are protecting. So the greater the primary current, the greater will be the operating current, the greater the flux, and in turn, the faster the disc will rotate. You can see here, as the disc rotates, it carries with it the relay operating contact, and this eventually is brought up against the fixed contact, so closing the tripping circuit. This is the well-known inverse time characteristic as shown by this family of curves. The time for contact closure is shown on the vertical axis, plotted for different values of relay operating current. The higher the level of fault current, the quicker the operation of the relay. Moreover, for any particular current value, we can adjust the operating time by adjusting the time dial here. What this actually does is to change the distance that the moving contact must travel. As the family of curves indicates, a time dial setting of 0.5 indicates the shortest operating time, while a number 10 setting will give us the longest operating time. When reading these curves, please remember that the value of current along the base is expressed relative to pickup current, that is, as a multiple of tap setting. For example, supposing that the coil tap is set at 2 amps and the relay current is actually 10 amps, that is, 5 times the tap setting. Now, if the time dial is set at 6, we look at this particular curve and find that the relay will operate in 1.55 seconds. If the time dial is set lower, it will operate much faster. This particular characteristic curve is known as very inverse. When specifying a relay, it is necessary to indicate whether an inverse, very inverse, or extremely inverse characteristic is required. We can see the difference on this chart. The extremely inverse type shows the steepest curve. That means it has the slowest response for relatively low current levels, but in contrast, it has extremely fast action for higher current. The characteristic curve can be slightly modified according to the position of this damping magnet. But this magnet is set in the factory and should not be adjusted during normal maintenance and testing. The type of characteristic is sometimes indicated on the nameplate of the overcurrent relay. Check this out next time you're in a substation and perhaps speculate why specific characteristics are chosen. This schematic shows a typical tripping circuit. This is the trip coil which will operate the breaker. Sometimes this is operated through an auxiliary relay so as to reduce the current which must pass through the relay contacts. A seal-in circuit is normally connected across the relay contacts so as to protect against contact bounce or inadequate closure. When the time delay contacts touch even momentarily, the seal-in relay picks up and the circuit now remains securely closed through the seal-in contacts. Only when the breaker opens does this auxiliary contact open, thus interrupting the tripping circuit and de-energizing the seal-in relay. Often the time overcurrent relay includes an instantaneous element built into the same casing. As they must respond to the same CT secondary current, the operating coils are connected in series. The instantaneous relay tripping contacts are independent, wired in parallel with the time overcurrent tripping contacts. Thus, in this typical trip circuit, either contact can complete the circuit and trip the breaker. The instantaneous relay will be set at a relatively high value and will only operate in case of an extremely high-level fault. When the relay does operate, a target will drop for either the instantaneous element or the time overcurrent element. This will inform the operator that the relay has operated and help him analyze his system problems. Overcurrent relays are widely used throughout the power system, not only for feeder protection, but also for motors in industrial applications and for backup protection in other areas. When applying time overcurrent relays of the electromechanical type, 2 points that must be considered are over travel and reset time. Once the disc is rotating under fault conditions, inertia will cause the disc to continue slight movement, even if the current falls below pickup value. This over-travel could cause inadvertent tripping. Moreover, the disc will not reset immediately. In some relays, not until the operating current falls below about 60 or 70% of pickup. If a repetitive fault occurs, the disc may not have time to reset completely, and each repetition may cause the disc to creep forward, and so after 2 or 3 repetitions, ultimately trip. These limitations must be borne in mind when calculating relay settings. Generally, overcurrent relays are constructed as single-phase units, and several relays are required to provide 3-phase and ground protection. The same type of relay with similar characteristics but different wiring is also used for over and under voltage protection. Now at this point, let's take a break, and then we'll come back and look at directional elements, which are often used in conjunction with overcurrent relays. For now, switch off the tape and thoroughly review this material in your